Okay. Um, we'll follow this PowerPoint for our work in Chapter 12. 3 times during the content, I will stop sharing the PowerPoint and go full screen on the whiteboard, and we'll make some proofs of these principles that we're going to be talking about, and then and that'll be that. Okay, so let's begin. Let's begin. A summary of what's coming. That's for your reference. I'll post these slides like normal. Let's talk about fluid mechanics. We'll start with fluids at rest and then talk about fluids in motion. The first thing we got to talk about is density. This is not new, I think, but let's define density. It's the Greek letter rho. It looks like a P, but it is not. It's the Greek letter rho, R-H-O, as mass divided by volume. How much mass does an object have divided by how much volume does it take up? Okay, that's the density. Fantastic. Here's a table of densities. Not a whole lot of note here, just that there is such a table. It's in the book. If you need a density on any kind of assessment coming up, then I'll provide it for you. So not an issue there. A couple things worth noting are the fact that ice is less dense than water, which is not really news. Ice floats in water, but it's something interesting about water that almost every other substance, if you go from its liquid phase to its solid phase, its density increases. And water is one of very, very few that doesn't do that, that actually gets less dense when you go from liquid to solid, which is really important. Actually, it keeps bodies of water from freezing from the bottom up. They end up freezing from the top down because that's where the ice is, and then they start to freeze deeper as it stays cold. But that keeps the depths where fish and plants are living from freezing solid. So it actually permits overwintering of life in bodies of water, which is neat. The other interesting factoid is that on average, blood is in fact denser than water. We can, quibble about the salience of English idioms like blood is thicker than water, but in terms of density, yes, generally blood is denser than water. Just sort of a fun little bit. Okay. Let's talk about this square of fluid, a small surface area within. Imagine that it's a piece of plastic that is exactly as dense as water. So you can set it in the water and just, it'll float at whatever depth you put it, and it'll just stay there. And the fact that it stays there means that we know, yes, there is some force on that piece of plastic, on this small surface area from the water in which it is submerged, but the surface, this little piece of plastic, does not accelerate. So the net force needs to be zero, and equal forces act in opposite directions. Okay. They have to be perpendicular to the surface, because if there were some component, get the mouse going here, if there were some component along the surface, then that would tend to drag that piece of plastic up or down or to the side. There can't be any component parallel to that surface, because then the surface would move. So the force has to be perpendicular to this area and equal on both sides. The same is true vertically. If we've got a if we just take that piece of plastic and orient it so that it's horizontal, the same has to be true. There must be an equal amount of up force as down force, because we can just leave it there. It won't move. We can observe that. So the pressure has to, well, excuse me, the forces acting on that square 2dA need to again be equal and opposite, and the same. They need to be um, well, yeah, equal and opposite. One of them needs to be up and one of them needs to be down, so that the net force on that surface area within the fluid is zero, because it won't accelerate. And the same is true of this same vertically oriented area that we were talking about in the previous slide. Now, the fluid is pushing on that surface area. And if it's a bigger surface area, then there's more room for that fluid to push. Think about stress back from chapter 11. It was force divided by area. So yes, we care about the force, and in fact, yeah, since it's a bigger area, there's more fluid able to act on it, able to push on that area. So there's twice the force pushing down and back up on this larger area than there is on this smaller one. But because it's twice, right? The area is twice, so the force is twice. And that proportionality makes me think that the ratio between force and area is constant from the one to the other. And that's how we'll define pressure. The ratio between the force applied perpendicular to a surface and the area over which it's applied. The unit of pressure is the pascal. And we'll talk about why that's the unit of pressure in a minute. The units are, I mean, 1 pascal turns out equal to, well, it's a force divided by an area, so it's a Newton per square meter. Okay. How much pressure is there? This is our first principle, and we'll derive it, and it'll look like a thing to calculate pressure. But then we can analyze it in a particular way, and it's the first of our principles. So here's the slide, and now we've got to prove it. Okay. Suppose we have a container with some fluid in it. So we've got a cylindrical container with some fluid inside. Let's talk about this very small disk of fluid at the top. At the top of the stack of fluid, there's a disk that has some area and some thickness. It has some volume. And because this is whatever fluid it is we're talking about, it has some density, and it's occupying some volume, and therefore it has some mass. That fluid is at rest, though. It's at the top of a stack of fluid. You set the stack, and then the top layer of that fluid, if I stop rattling the bottle, stays at rest. It doesn't accelerate up, it doesn't accelerate down, it doesn't accelerate to the right, it just stays there. So if it's not accelerating, then the net force on it must be zero. The net force on that thing must be zero. There is gravity. Its mass times g. And then and that's down. So, and there must be, because we know that gravity acts on this much fluid, there must be another force holding it up. And it's the combined force of the pressure from the rest of the fluid pushing up. Equals pressure, let's see, hold on. For pressure P is force per area. So note that this is a P and this is a rho. So the other force is the pressure times the area. Whatever, there's gravity coming down, sure, but then there also must be a pressure up. Now let's say this is, a container that's been evacuated. So this is completely vacuum. There's nothing here pushing down on the top of that surface, not like there is in the slide. So the only force from fluid is the fluid that's below the thing in the container. I'm just gonna F the pressure, I guess. Okay. So this means that mass times gravity equals the pressure times the area. Now the mass, let's unpack that, is rho times the volume. And the volume is the area of the disk times its thickness. I'm going to call it, what am I going to call it? I'm going to call it H. But that's an area on both sides. And the pressure that must be pushing up from below on that disk of fluid is rho GH, where H is the thickness of that fluid. In other words, the height of the fluid above whatever point it is we're talking about. If we were interested in making a chunk of that much fluid, well, there would still need to be a force, and it's a larger H, but that's fine. Our formula still works just fine. The density times the volume, it's a bigger volume, fine. Same area, but bigger H. All right, so that means there must be a larger pressure because there's more fluid here that we need to hold up. So the deeper we go, the greater the pressure, which matches our experience. Now, what if this were not vacuumized? What if it were not evacuated and there was air above that? Now, at the surface of this fluid, redraw the fluid surface here. At the surface, that surface needs to be exerting some pressure to hold up the air that's above it. Just like that section of fluid there, that surface needs to be exerting some pressure to hold up this chunk of fluid. Well, this area here needs to be exerting some pressure to hold up that all chunk of fluid, all of the air on top of this thing. Okay, well, we could use this same theory. We would just have to change the density, because the density of air or whatever is on top is theoretically different than the density of whatever fluid this is. But all of this goes the same way. This open to the air lets us say something about, all right, well, if there's some external pressure, P0, we could call it, the environmental pressure, the pressure of the air, of the surroundings, plus that there's some pressure as a result of the external environment and the depth that we are submerged to within the fluid. And I'll write rho FL for fluid to contrast that from the density of whatever the environment is. And that is that formula on that slide that I just navigated away from. So let me go back. Oops. Okay, so the pressure is the pressure at the surface plus whatever depth we are. Now, the pressure at the top of each column is the atmospheric pressure, this environmental pressure that we were just talking about. There's a different amount of fluid in each tube, each column. Each one has a different shape. It had a different volume, so there's a different mass. That's fine. The pressure as applied to the top surface in each of the 4 columns is the same atmosphere. And the height of each column is the same, because the pressure in the fluid at each depth within a fluid is the same. Changes in pressure are communicated throughout. In other words, there's nothing about this depends on the source of the environmental pressure. If we, so if we come along and just push down, we grab a lid for this container and we push down on this fluid, what it effectively means is like, well, everything above feels heavier because there's an extra force pushing down. That doesn't only affect the fluid right at the top, because what we're doing is changing the environment, and that change in the environment is immediately communicated to the entire depth of the fluid. If we're down here at this other surface, the pressure that it's going to need to exert up to keep this all at rest is more, because we've increased the atmosphere, the environmental pressure. So changing the pressure here, applying a force, an extra pressure here, immediately, boom, carries that information through the entire rest of the fluid, and that is Pascal's principle. We name that after Blaise Pascal, the same Pascal that is the unit for pressure. And his principle is that the pressure applied is transmitted undiminished and immediately to every part of a fluid. We apply a force to the top, and that additional pressure is communicated the entire way through, the entire way down. And if there were another shape, it would be the entire way through. And that's the principle behind like a hydraulic lift at the auto mechanic. We apply some force here to a small area, and because the pressure that we've added is transmitted undiminished to all the rest of the fluid, that same pressure over a much larger area, same pressure, bigger area, the only way that's going to work is if the force increases too, because the ratio between them has to be the same. If we double the area, we got to double the force. So the wider the area over which we spread that fluid, the more force we can exert. And we can lift a car that way. And that's Pascal's principle. Just take a quick peek what the next slide is. Okay. The P0 plus rho GH, a lot of the time we don't, like, the pressure of the atmosphere is the atmosphere, right? And what we care about is pressure above and beyond that, because we're all here living in the atmosphere, talking, comparing everything to the pressure that we normally feel just every day seems very strange. We care about pressures above that. So we can make a distinction between the actual pressure, including the air, and the gauge pressure as measured above the environmental pressure. The excess pressure above atmospheric is called gauge pressure. That's whatever the pressure gauge, the device we're using to measure the pressure above the atmospheric pressure. Whatever that instrument is reading, we call that the gauge pressure. Which means the gauge pressure could be negative if the actual pressure here were to be less than atmospheric pressure. That's totally fine, right? If the actual pressure here were, if P were less than, no, I'm sorry, P isn't going to be less than, I'm all confused now. The absolute pressure is still greater than atmospheric pressure, but the gauge pressure could be less than atmospheric. If you got some kind of partial vacuum or something, like the slide says. If we pump some air out, then the local pressure, rho GH, is less than the atmospheric. Wow, just an example of a pressure gauge in another unit. Bars. 1 bar is 10 to the 5 pascals. Okay. So that's our first of 3 principles, and I'll stop the segment there, and we'll pick up here in a second. We stop sharing, so the screen shows up one more time. You get the whole deal there, and that's where we'll stop it for now.